Our next speaker will be Dr. Javier Ortega Jerez. We welcome Dr. Javier Ortega Jerez, a structural engineer and researcher at the Spanish National Research Council, specializing in the seismic vulnerability of vernacular and heritage structures. He holds a PhD in civil engineering and co-founded FENEC along with Marietta Garcia Nunez. In this talk, Dr. Jerez will share insights from his work on the seismic vulnerability and risk assessment of unreinforced masonry buildings in large territorial areas, such as cities, using simplified methods. He will also present some examples of seismic analysis of individual masonry buildings using non-destructive testing and finite element analysis, drawing on field experience at major heritage sites including the Shah Mosque in Iran, the Alhambra in Spain, and the Giro Castra in Albania. His field-based approach offers valuable frameworks for improving seismic safety without compromising architectural integrity.
Thank you, Jonso. Well, first of all, I'm very excited to be here and talk to you. Thank you so much for coming. Thank you, Studio Nyandak, for inviting me and proposing to speak about this topic here. Thank you for the Library of Tibetan Works and Archives also for hosting us. It's been such an interesting couple of days. It's been great listening to all your presentations. So what I would like to talk today is about the seismic vulnerability assessment of unreinforced masonry structures. I will be focusing on existing structures, no new construction. Try to explain different approaches that we should follow depending on the scale, on the type of structures. But I will look into that later. I will go on during the presentation. First of all, maybe I would like to acknowledge something that Paul already commented in his presentation. Unreinforced masonry buildings are particularly vulnerable to earthquakes. They tend to suffer damage, and this happens because of the type of material that we are dealing with. At the end, masonry, as you may know, is a composite material. It's composed of a masonry unit, which is normally stone, adobe, another thing, and a mortar that puts the units together. And because of this, masonry is typically has very limited capacity in tension. If Paul was discussing about also there is a shortage for concrete structures, it's even more a shortage for masonry structures. There is another thing that happens with masonry structures and traditional ones in the difference with reinforced concrete is, as you might have seen in Paul's presentation, normally in reinforced concrete structures, the masses are concentrated on the floors. In masonry constructions, it's the opposite. The masses is concentrated in the vertical elements, in the walls. So they behave completely different. This is the type of damage that is more common that we can see when after an earthquake where we have this kind of unreinforced masonry structures. Because of the limited tension capacity, we have this type of out-of-plane failures. And because there is normally not anything that is tying all there is a lack of connection between the walls. There is nothing that is tying all the elements, the vertical elements that are the resisting elements. We have also this kind of separation between the walls, leading to this kind of brittle failure that can cause a lot of damage. And there is another important thing in masonry structures, which is this possible disintegration of the wall because of the poor quality of masonry, the type of stones that maybe are more rounded. There is a lot of things that can lead to this kind of disintegration, causing also destruction of the building. And then we have also another kind of failure which is less brittle, and maybe we try to look more for that, but it also causes a lot of damage, which is the in-plane damage. And then when we guarantee that there is no disconnection, maybe we can also suffer this kind of damage. Okay, thank you to Dechen and Cheyenne. Nice presentation. We have already discussed a little bit about this. I don't think this is the seismic hazard map of India. I was not able to find it, but you have already seen it. But more or less it's the same, and it is a seismic hazard map for an earthquake return period of 2,475 years. And we can see that the Dharamsala is in the highest risk area, and it's the highest hazard. And then I also want to build upon on what Shayan was describing about our understanding of risk. The more simplified understanding of risk is a combination of these three factors. We have the hazard, which is somehow unavoidable. It's something that is there, it's part of the place where we are. We have the vulnerability and we have the exposure. And the exposure is something we can also work a bit, and we have discussed in this also a little bit in the previous presentation. We can work of drilling exercise, how to interact with exposing less our population, our buildings to the damage, but there is not something that us as architects and engineers can do, is working on the vulnerability, because we can this is where we can put more of our efforts, because it's how we can make our buildings more safe. At the end, vulnerability is understood as the proneness that a structure, an object, has to suffer damage after a given earthquake. This is something we can actually use our knowledge to improve, and this is something that it has been known always, no? And so I would like to go back and talk about the concept of, I don't know if you heard of it, the concept of local seismic culture. And this is something I studied in the past, because now we can build on concrete or steel, or what we tend to understand better as a way of being, of building more resilient, but we haven't been always using these techniques. So in the past, buildings have survived earthquakes. So I mean, masonry, timber, and other traditional systems have also the possibility of surviving earthquakes. They have shown the capacity of doing that. So it's a question of how to build them. This concept builds on the idea that if the local communities are exposed frequently to earthquakes, they tend to develop traditional earthquake resistance systems, because they see what is the effect of the earthquake in their buildings. And they see what buildings, is a trial and error thing. They see which buildings have survived, they see which buildings have suffered damage and been destroyed, and they tend to copy the ones that have performed better. So this is an empirical idea, no? But however, in those places where the earthquake might be devastating, but they are not so frequent, we tend to forget what has been good in the past. And this is what the difference between, as Professor Touliatos from Greece once said, no, that these diagrams are from him, and they were the difference between a seismic prevention culture. We have earthquakes every 70 years, more or less a generation span. We understand this. Or the culture of repairs. We have an earthquake, we just see the damage, we repair, then we forgot what is the effect of earthquake in our structures. So we have been studying this, and we have seen earthquake resistance system all around the world, and they have we have seen this in all. This is a seismic hazard map, a global seismic hazard map, and normally these systems are observed in places where you have frequent earthquakes. We can actually see also a very rough seismic base isolation system that they were developed in Iran, and normally they are all based in the same concepts. I will try to go a little bit more on about them now. You also have here in Dharamsala, I was told that you have the Katkuni system, which is also a timber lacing system. It can be understood as an earthquake resistant system. They are always based on the same ideas, which has to do with the damage that we observe when we see a building. So what we need to do is to tie the building together. We need to tie the structural elements. So we know what they have normally done is to use timber. And that's why many times in ancient buildings, you see a masonry wall, and you also see some timber beams, because they are trying to tie so you prevent this out-of-plane failure that we were talking before. It can, maybe sometimes they only use that in the corners, which might be enough. Also, you use the coins, so making the corners also a little bit more resilient, so you prevent the failure to happen in the corner, and you prevent the separation. Or ties. Sometimes this is not so common here, but in some places in Europe, ties are very, like Italy, you can see ties all over the cities, and you see always this connection in the end. And this also serves to tie in, to connect different structural elements. Another idea that you can have, and how they try to prevent buildings to be damaged during earthquake, is to stabilize the structural elements, so reinforcing the walls, also by using timber lacing masonry, or in using this brick masonry, so you divide also the wall into different parts, using different materials. Also the floors, you try to stiffen the floors, or also you use timber frame to connect walls. Or the other type that is more common to use is buttressing, when you buttress a structure, so you tend to avoid you counteract the possible out of plane failure that a wall can happen. So you add more mass, you make it thicker, or you put a buttress, or you have a reinforcement arch, something that will limit and will avoid this overturning. We did this work in Portugal. We tried to understood if this is something, but Portugal is a country that also doesn't have so frequent earthquakes. They have had very devastating earthquakes in the past, but people has also tend to forget a little bit. They are not seismic aware of the seismic risk, so it's difficult to find all these techniques in this place. We have identified some traces, but we have lost the seismic awareness. And I understood that maybe in Dharamsala it might have happened, because if the last earthquake was in more than 1 century ago, in 1905, as what Dechen was explaining, maybe we have also forgot what is the effect of earthquakes. And if we are not, maybe now we have seismic codes, something that regulates, but the vernacular non-engineered buildings, they don't rely on the codes. You do what you understand is empirical knowledge. So, well, that's a little bit the idea of how people has tried to build in the design with the seismic awareness, but this has been empirical knowledge, as I was saying. This is only visible trial and error process. If we want to see, actually, we want to understand what is the behavior of a unreinforced masonry building, is very challenging. This is a work I like to discuss from some colleagues from the University of Minho when I was in Portugal. This is a seismic second table test. It's nice that you have all discussed previously all these topics, because I don't have to explain them. But basically, you can induce an earthquake in a table. You put the building on top, and you can induce an earthquake, an acceleration of any input that you want. And they did this experiment with these two very simple structures, brick masonry, stone masonry, and they knew everything about the type of materials they use, the geometry, and the earthquake input, so the accelerations that they are going to induce. And the graphs there show they did a blind prediction contest, so they invited a lot of experts in masonry seismic behavior to try to guess what would be the maximum capacity of these structures. And there you can see there were all kind of different predictions, and none of them got it. So I mean, it's a very complicated topic, because it depends on many factors. There are some good things, like maybe all of them under predicted the capacity, so at least we are on the safe side. But you can understand that the challenge is huge. It's difficult to understand what is going to happen if an earthquake hits. And this is even more challenging if we don't know anything about the structure, because this is already there. So I like to show this slide, because if we don't have data about the existing building, and if it's already difficult to know what is the behavior when we know everything about the building, even if we don't know anything, we don't know the material capacity, we don't know the geometry. Geometries are very variable in historical buildings. We don't know construction details. Okay, this is a reinforced concrete, but we don't know also the connection between the elements. We don't know the loads that are passing through these buildings, and we don't know the damage that is already there. So this even makes it more challenging. And I would like to discuss like two approaches of how can we try to assess or have an initial idea of how these buildings and this building behaves. And I would like to distinguish between two types. which has to do with the scale. When we discuss, when we are trying to understand the seismic behavior of a building, of a single building, for example, a monument, an important building, maybe we can have detailed approaches. So we can do testing, we can do inspection and advanced analysis. But if we want to aim to a large data set of buildings, we cannot do the same. We don't have the resources. And this is what I would like to differentiate now. If we are aiming at this kind, these are buildings in Portugal, but if we are aiming to this kind of buildings that are non-engineered buildings, traditional ones, we don't have the time, and the resources to address each one of these individually and understand exactly what is the capacity of each of them. And we also have these kind of buildings here, no? In Dharamsala and Tascar we are going, they are small buildings. We cannot do an advanced analysis of all of them. It will take a lot of time. And also the scale. We are not talking about 1 to 10 buildings. We are talking about hundreds or tens of buildings. We need a different approach. So that's what I would like to divide this presentation. When we have the building scale, so we are addressing one monument, we have a set of tools to try to understand how the building will behave. Or if we have a larger scale analysis, an urban, and in this case, Chayan was explaining it very well, we need rapid screening methods, something that can have easily, we can detect which are the most vulnerable elements in our data set and maybe put more effort on those. So the approach is completely different. These ones are based on typological approaches. I will start with those actually. In these ones, Chen showed some FEMA forms. In my case, or in other case, you have several. I will talk about. But basically, the main tool you have is just going and to the field and complement some forms with few details of the buildings that might be enough to have a preliminary understanding of how the building will behave in the case of an earthquake. So basically, it's just this is rapid surveying methods that you can be taking information about each building, and then also localizing this building. GIS tools are very useful for that. So and then we have this kind of databases. So each building has like an identification number and a set of building parameters, material parameters, so we can individualize each building with data that we can only use our eye from the exterior, because also it's going to be very difficult to get inside all these buildings. Sometimes we even need to use some Google Maps or some other kind of tool because we don't have the capacity to visit all these buildings. So the information that we need to take has to be very simple. And I would like to, as an example of this kind of rapid assessment tools, I would like to discuss the one method that we developed that was particularly aiming at vernacular architecture of unreinforced masonry or earth architecture. So the first thing we needed to do is to define the parameters that we thought would be more decisive in defining the seismic behavior of these buildings. But they needed, again, to be simple, something that we can understand and take and classify with a simple visual inspection. So, okay, I'm not going to go through any of them, but it's things like the slenderness, the thickness, the number of floors, the amount of openings they have, the type of material. We have seen that depending on the regularity of the blocks, the type of bonding they have, the mortar, how they are arranged, we can have an estimation of how good is this material and how good it will behave in the case of an earthquake. Also, how well is the connection between walls, or how is the horizontal diaphragms. If the beams are well inserted in the walls, if the diaphragm is rigid enough, is flexible, and this is the first thing we need to decide. And then the other thing we need to define is the class. This is just a system. Okay, we have this type of material. from A, B, C, or D, which kind of material it is, A being the one that would behave better in case of an earthquake, D being the one that will behave worse, so a very irregular type. If we have a very irregular masonry, then we will classify as D. If we, in the case of the horizontal diaphragm, is the same. If we have diaphragms that are poorly connected and they are flexible, well, they will become A and D. If they are well connected, they are rigid, then we can classify them as an A class. We also gave importance to each of these parameters because we found out that they don't have the same importance. It's not the same. The type of material doesn't have the same effect as, for example, the maximum wall span. So we also measure them according to the weight, and then we can score them. It's very similar to the FEMA system that Chiang was explaining before. Then we will have an index that normalized can be between 0 to 100, and each building will be, if 0, it's no vulnerability at all, 100 is very vulnerable. Of course, we will never move because there is no building with no vulnerability, but okay, this is the result. And then with this information, we can map our results, and they can give us very valuable information about how we should act in an urban scale. Okay, this is an exercise we did in an historical city center in the south of Portugal, in the city of Villarreal de Santo Antonio. We first did this, since this methodology was aiming at vernacular architecture and reinforced ones, we only focused on those buildings. So here is the buildings that we inspected. It were like around 300 buildings. And then we carried out these surveys, and we could identify which ones were the most vulnerable. We gave them a rating of this index that ranges between 0 and 100, and we can locate, thanks to this mapping, we can locate where are all these buildings. Of course, this is a rapid screening method. We are not interested in knowing, like, okay, this is the building that is going to suffer this specific damage, and this, but it's very informative as to understand why is this building identified as more vulnerable, and also in terms of percentages, how many buildings are more vulnerable, and we can have an idea of what is our building stock and how will our building stock perform also in probabilistic terms. So, and one thing that is good about these methods is that they have been tested also after earthquakes. So there is like thanks to post-earthquake observations, we have been able to develop some formulas that correlate the index with a probability of suffering a specific damage for given earthquakes. So I'm not going to go into detail into these formulas, but these are empirical formulas that are developed, and they correlate index, so vulnerability, with the damage after a given intensity or a given earthquake. And this is very helpful because we can estimate, for example, for different earthquakes. This is in the graph that we have on the bottom left. We can estimate, like, for an earthquake of a given intensity, for example, a 7, we can estimate more or less how much damage will our building suffer. Again, probability. It's not that, okay, I know 30 buildings will collapse. No, we have a probability that this percentage of buildings may collapse or may suffer damage of scaling 1 to 5, being 5 collapse, being 0 no damage. And with this information, we can also have an understanding of possible buildings that will suffer collapse, how many buildings also, and if we know how many buildings can suffer collapse, we can also estimate even what is the probability of casualties that we might have, what is the probability of homeless people that might, and this can inform urban strategies on how to act. And it can be also informative to see how can we retrofit these buildings. So we devoted also some time to understand how all these previous identified construction techniques that are supposed to be earthquake resistant. We also devoted some time to try to analyze better how efficient actually they are in reinforcing and strengthening our buildings for seismic retrofitting. So in our case, these are the techniques that I shown earlier. All these timber lacing, the timber ring beams, ties, quoins, buttressing. We did some analysis. Not going to get into detail, but we did some numerical analysis to understand. Okay, yeah, this is identified as an earthquake-resistant technique, but how much and which one is actually more efficient? So we did this analysis for many of them. We also did experimental studies. So we had these walls, unreinforced masonry walls, and we compared and then we reinforced them with ties and with timber. And we again did the same experimental studies. In our case, this case is a simple, more or less simple. In the case that what we pushed is we pushed the building with an airbag, simulating like the horizontal action. So we pushed our wall, and we see what was the resistance and how much it changed if it had a timber reinforcement or a steel reinforcement, or if it doesn't have anything. And we were able to identify that actually these techniques have an important effect. They increase both ductility, so the capacity to deform that Paul explained so well, and they also have they also increase the capacity of the building, so the maximum load that they could sustain. So based on this, we can also know if we implement some of these techniques, some of them are more easy to implement as retrofitting than others, but we can know that if we implement these techniques in our at an urban level, how much are we reducing the vulnerability of our building stock in our given area. So we did this exercise. We decided, okay, let's try to simulate that in our more vulnerable buildings, we are trying to reinforce the floor-to-wall connections. We are trying to reinforce the connection between the wall and the floors. We also want to stiffen them. Okay, a set of, and we see what is the impact and how it reduces the vulnerability. Okay, this is a theoretical example, but this is to show how these rapid screening methods can be very useful to understand how can we invest. Because we can understand what happens if we implement, for example, a retrofitting technique that that helps to reinforce connection between the wall and the floor, and how much does it cost? And how much does it cost if we implement in 20 buildings or in 50, which we think are the most vulnerable? And how much will it cost us to do that, and how much impact will have according to different earthquakes? Of course, if we never have an earthquake, it will just be money that we are investing, but we are supposed that we will have earthquake in the future. So we can say, okay, if we have earthquake, we will reduce the vulnerability of it. They will suffer less damage. We will have to invest less later for reconstruction or for repairing. So we can do this kind of analysis that are very helpful in urban terms, no? Or in regional terms. Okay, and now changing the scale, this will be now a different approach. Now we have a big building, we have an important building, we have the resources to apply to the study of the behavior of this building. So now our tools are going to be different, and we have the opportunity now to do a detailed analysis. In this case. Okay, here is this. In this case, I will go again to the previous idea that we can do any kind of analysis to a given building. There is multiple possibilities of trying to understand what will be the seismic behavior of a building. We can here I'm just showing some. There is a limit analysis. I'm not going to go through them. Just equilibrium. We can do advanced numerical modeling with finite element analysis, but our ability to trust the results of this analysis relies very much on our capacity to understanding and characterizing these structures. I will go, because this is another example, I will go later more in detail, but we can have a very nice approach to simulate the behavior of these buildings. For example, a very detailed numerical model, but if we haven't characterized the material properties, I will go back here. if we don't know what are the material characteristics, if we don't know the real geometry, or all these aspects that we were discussing before, at the end, the capacity that we are estimating is just a guess. Okay, it will always be a guess, but we can reduce the uncertainty about this guess. So this is why non-destructive testing and inspection and all these activities have a big importance when we are trying to assess the capacity of a masonry and historical building. I will just discuss some of them. For example, we have the possibility of reducing the uncertainty about the material behavior using some tests. In this case, it's sonic test. We just because of we can quantify the velocity that of a wave that goes, a sonic wave, a acoustic wave going through a material, and this is correlated with elastic properties. Okay, we have already an estimation. We know the elasticity of our material. This is something we can do. Another thing we can do is to get advanced surveying systems to get a detailed model, a detailed 3D model of and a good understanding of the geometry of these buildings. This is an example when we work in an important monument in Spain, in the Alhambra, in Granada. Before we did the analysis, before we could go there, we did a preliminary analysis, and we used just information from books of what was the geometry of this building. And this is our initial model. And then we have the opportunity to go there to do this is Marietta, actually. You will not recognize, but this is Marietta doing a laser scan of the tower. And actually the dimensions were completely different. The heights, the thickness of the walls, this was done in a very thoughtful and thorough way, so we did all the interior parts, the exterior parts, so we could understand exactly what are the dimensions. And all these things, they have an influence in the final seismic behavior. We also did the damage mapping. All this influence the behavior of the structure. So we need to devote time to inspection and to what we could not do when we have large-scale analysis, right? We need to do this if we are aiming at an individual building. And there are many things, possibilities to do that in terms of geometry. For example, this is another case. We did the previous one was with a laser scanner. This was done just with a drone to get the overall geometry of the outside of this church, and then we did also a photogrammetric survey, so we took a lot of pictures from the interior, and at the end you can have a very detailed model of the building, which includes which is very informative because we will have, for example, the exact dimension of the wall thickness, and this is something that will definitely have an impact on the seismic capacity of this building. So, to illustrate this point, we did this exercise. This is the structure that I showed before. It's a set of a bolting structure in Greece. We had the opportunity to go there. We did this sonic testing to get to estimate the material properties of the building. We did also some dynamic testing. Paul also mentioned this. All buildings have a frequency of vibration. They move naturally. They have these are the natural frequencies of the building. They will respond to earthquakes according to this, as Paul explained. We can capture this experimentally. We can know which are these frequencies. So we did this, and with this information, with the information of the natural frequencies and the information of the material properties, we put all this data as an input of our numerical models. And then we had the opportunity to run analysis. Okay, this is a process that is called, we call it model calibration, because we built up a model and we don't know if it actually represents or simulates well the structural behavior of a building. One way of understanding if it represents and simulates well the structural behavior is precisely with these natural frequencies. We can do a model analysis of our model. We can see what are the natural frequencies numerically, and then we can compare them with experimental ones. If they both match, then we can be a little bit more confident that our model is simulating well the reality, and that our model can actually represent what the building is going to suffer in case of an earthquake. And then we can run our seismic analysis. And this is what happened in the pictures in the right. In this case, we are comparing. There are two curves. One is the dotted curve, and the other one is the continuous black curve. This simulates well, okay. Let's say the vertical is the load, the maximum load that these buildings could take. So the dotted one is our first guess before going there, before taking all this information. So if you don't have this information, actually you are and you are thinking that your structure might don't have enough capacity to withstand this earthquake. Once we went there, we calibrated our model, we actually understood that actually it has a higher capacity than we were thinking. It can be the opposite. Maybe we are actually overestimating the capacity, or we can underestimating the capacity. We don't know. But this is in this case, it turned out well because we didn't have to be so invasive when deciding on how to retrofit these buildings. But in any case, once we have these models and we trust on them, we can try to introduce also maybe retrofitting techniques. So in this case, for example, we try to put some ties, and we can try to compare what happens if we put some ties in the building, if it will behave better, worse, if we improve the capacity. And again, it's not about, when we are working with heritage structures, it's not about obtaining the most resisting system. It's not about getting the maximum, the most resisting building. It's about making the building resisting enough. So is it enough with this retrofitting? Maybe we don't need to do more. Because when we do retrofitting of historical structures, we also need to be a little bit careful about how not to be so invasive, trying to maintain so it's this difficult balance between safety and respecting the heritage values of the systems. No? And just to finish, I think I'm good in time. Just going back to this and try to make a little bit circular presentation. Okay, yes, as in the first slide I showed, unreinforced masonry can be particularly vulnerable to earthquakes, but they have also shown that they can withstand earthquakes. So it's not a question of, maybe they can be less resistant than other construction systems, but they can be resistant enough. So it's a question of knowing and understanding how they behave, and that's why we have different tools to assess them. And based on this and a good understanding of masonry structures, we can both understand if they are enough, if they are capable of resisting the earthquake that they are going to be facing, and if they are not, we can also try to use these tools to promote a nice retrofitting strategy that is adequate for these buildings. So I think that's all from my side. Thank you so much for listening.
We'll now welcome our next speaker, Marietta Nunez Garcia, an architectural engineer and expert in structural analysis of historical buildings. She is the co-founder of FENIC, a nonprofit dedicated to non-destructive testing and conservation science, and holds a master's in structural analysis of monuments and historical constructions. In today's talk, she will delve into the structural and cultural importance of vernacular timber architecture. She'll introduce on-site diagnostic tools for evaluating wood, adobe, brick, and concrete buildings, and present case studies from her international work and field observations as well in Dharamsala.
Thank you. Thank you very much. Firstly, to the library for having us here today and inviting us. Also to Studio Nyandak for making this possible and inviting us here, both to be here at the conference, but also like to go to Zanskar and to like be doing like some studies there. And also like thanks to his team who have been very kind like in organizing all of this, and also have provided some of the photographs that I'm using in my presentation. So I will not be talking about earthquakes, that I think that has been covered today. I was asked to talk about the conservation of timber structures, and also about the testing techniques to better understand them. So what I have often found in conservation of timber structures is that there is not usually a lack of engineering knowledge to like determine the capacity of a timber structure, or how to reinforce it, the main problem for their conservation. But sometimes it's a lack of understanding of all the other things that go beyond engineering that make our timber heritage special. So I decided to focus here on the context of timber structures, because sometimes bringing into the engineering design these aspects and how our designs impact the value of the timber heritage is something that is not often like discussed. And this is something that can be discussed by many stakeholders, not just architects or engineers, but also like managers and users. So that's what I will be talking about today. So traditionally, when we talk about heritage, we think about more highly decorated, artistic, or historic buildings that we associate to monuments. But we also have like different types of heritage that might be like less decorated, less historic, but ended up composing our vernacular architecture and are part of our lives and of our culture. So usually and traditionally, like those highly decorated buildings or that have this artistic or historical value might be protected, but the other ones, the more simpler ones, might not. So how do we understand where to trace the boundary in like about which aspect and which buildings need to be protected and which others like might not have a heritage value for their conservation? This is not an easy task, but I will try to discuss this a little bit here today. I bring this example of two opening frames, a door and a window, that are very different. So we have one very old and highly decorated wooden door in Madrid, and we also have like a much more simple window frame in a historic farm in Vancouver Island in Canada. So while traditionally we would expect the door and the building in the left to have a degree of protection that will require us to do certain types of intervention and like respect this door and not replace it with a new one, often we find that the elements like the window in the right do not have a special type of protection that will encourage professionals and other stakeholders to keep them. So while they are two very different types of frames, they are both very important in their context, because the window in the right talks about the context of an era, a way of living, and this is the first farm that was ever built like, and it's still functioning in this island. So like all the constructive details, they are all talking to us about how they used to like build timber frames, how life was in a farm, in a traditional farm, and which tools were used. And that's knowledge that is lost, and many of these buildings can bring us back this knowledge. So we can no longer just look at artistic or historical values as the only way of understanding what heritage or which aspects of heritage need to be protected, but we need to take a wider look at things. And actually, this has caused a change in paradigm in conservation of historic structures. While traditionally we have seen and developed and practiced a fabric-centered approach that was very much focused on preserving the materiality of buildings, all the buildings, artistic buildings, and keep as much of the building material as possible. Now we are going beyond only the materiality of the building because we need to understand the building in its context and how it's appreciated by a society, the people that use that building or that for whom that building is important. And now we are starting to study heritage also from the point of view of values, the values that our society has, and the people that actually like use our heritage. In this example here, I show to the left, this is Pedro, he's a carpenter in Spain, and he's trying very hard to do like timber repairs in a historic wooden roof, keeping as much material from the original roof as possible. And to the right, we have a course on traditional timber techniques in Sweden, and they are building a new frame using traditional knowledge. So I once saw a conference in which a philosopher opened with a speech, and he said something that I thought it was very interesting. And he mentioned how we usually value very old, fragile objects like a porcelain cup that has withstood like many, many years and has arrived to our days without breaking. And we can face that object and we see it in front of us and we are amazed. No, it's so old and it was done like so many years ago by someone like that lived so many years ago. But we do not value the fact that oral knowledge is very fragile and can be as fragile as porcelain, because oral transmission can be very easily broken. And this knowledge is part of our heritage, and we need to start taking care of it just as much as the porcelain cup, because it's as fragile as the cup itself. So when working on historic timber structures, we need to start taking into account also the fact that skills and knowledge are part of the building that we are working in, and we need to try to preserve them as well. So I will just very briefly name the types of wooden heritage, so this will support the rest of the presentation. So this is actually different types of heritage in general. So we have natural heritage, and we also have like or cultural heritage made by us, which is, can be like tangible and intangible. And understanding as intangible that which lacks physical substance, no? And the tangible heritage can be both movable and immovable. I have here like just some examples or natural heritage. These are like wood examples, but they are very much connected because like we source wood from our forests for our buildings, no? Natural, like it's our forests or landscapes or trees. Or cultural, tangible, immovable heritage are our architectural buildings, the structures, the decorative finishes that are like on them and cannot be moved. We also have all cultural, tangible, movable heritage that we have like structures that can be disassembled and reassembled as much as we need. We have also like maritime heritage or paintings, sculptures, instruments, and pieces of furniture. We also have a lot of submerged tangible heritage, and for wooden heritage we have there are around the world a lot of archaeological sites where archaeologists have to actually wear special diver outfits. I find this fascinating, but not useful for today. But I like to show this picture, sorry. And we also have our cultural intangible heritage. And I am showing here just 4 examples of intangible heritage from different parts of the world that are related to wood and to wooden structures. These 4 examples are types of traditional intangible heritage that have already undergone a process to be recognized and included in the list of representative intangible cultural heritage of the UNESCO. No? But there's a lot of every culture that has wooden structures have this kind of intangible cultural heritage. No? So from assembling the structure to scribing the details of the joinery, and also even using timber rafting down to the left as a means to transport wood along a river. That's all part of our knowledge and how we have always built these types of structures. So in order to talk about the importance between tangible and intangible heritage, I show this example from where we are, from Spain. And this is these are salterns. This is a landscape north of Spain, and what you are looking at are timber structures that are used to extract salt and produce salt traditionally. This place has been a saltern for hundreds of years, and until recently, when several decades ago, it was very much used, but several decades ago it was really in danger of collapse, and it was neglected, and it was no longer used as salterns. So what you are looking at here is a picture of the salterns after a very thorough and very nice restoration that has undergone this site. But this restoration was only possible because there was one last family, only one, that knew how to operate the salterns. So thanks to good timing and being able to understand how these structures function, they were able to recover part of the salterns. This is only part of the salterns, what you are seeing here at the picture. So without the knowledge on how to operate them, we wouldn't have been able to recover these timber structures. They would have no use. The investment in restoring them without the function, it would not have been feasible. But now, they extract salt here, they can make money out of it, as they did all the time in the past, because this was actually a very important economical source in the region. And this process of conserving this structure would not have been possible without the intangible heritage that's linked to it. Actually, these structures don't only have associated intangible heritage, like how they were built, but only how to operate them. How you need to spread the water, you need to use the water canals, how to let it dry, and actually the salt is now very much valued in Spain for really high-end chefs, and it's part of our gastronomical culture. So this is just to say that these pieces of buildings, these structures, are not only just structures or a landscape. This goes beyond their physical reality, and is much more, and is part of an intricate system of a society. And so are the monasteries in Sanskar that currently Studio Nyandak is so thoroughly studying. So we will not only have to study the buildings themselves, but also all these other aspects, all these contexts that make the buildings the reality that are now, and the values that they have, and why they are important, so we can understand how can we intervene in them without removing these characteristic aspects from them, and without harming all that is not physical. In this picture here, I'm just showing a detail of one of the canals of the salterns, and this is something that is not usually discussed when we talk about traditional heritage or assets definitions at least in Spain. No? So the fact that we need to run water through these canals, or knowing that you cannot remove the salt from the surface of the timber or like you might be able to damage the wooden canals. It's part of heritage. So we cannot limit wooden heritage to buildings. We also have cultural heritage and all that goes associated to the structures themselves. So when we talk about cultural heritage, I like this particular definition. I will just very briefly read it to you. And the definition says that cultural heritage are those inherited resources that people identify and value as a reflection and expression of their evolving knowledge, beliefs, and traditions, as well as their understanding of the beliefs and traditions of others. Reading this definition, we can reach the conclusion that heritage is not just physical assets, it's not just monuments, it's not just protected resources, and it's not just elements of the past, it's dynamic and ever-evolving. So how can we know what is heritage and what is not? Because this definition seems pretty subjective, no? Like, how can we identify those elements that are not within the building, but we need to be like paying attention to integrate them in our heritage conservation process, no? How would you know if they have value or not? So what we usually do is we study the building from different points of view, and we try to determine which values does this structure or this building has from different perspectives. So we can have many different values for a heritage asset, and not only like buildings, but any type of heritage asset. So this can be like, you can see here some of those: cultural, social, historic, religious, educational, aesthetic, many of them. And we can study our building and try to understand like what makes this building special, no? Heritage values have always been like in constant review. Like the first identification of heritage values, for example, did not include the religious value, no? And that was later incorporated as like as a society. We have realized that we had more values to incorporate within our system that we were not taking into account. Incorporating values into like our work methodology is always advisable. We don't always have the chance, we don't always have someone that can assist us in studying the structures or the buildings, because this should be like a multidisciplinary approach and research. We might not have the access to archives to look for historical literature, or we would need an archaeologist or an historian to do that. But we, even if when we don't have the resources, we can try to analyze this on our own, even if it's in a very schematic way. So I'm showing you here like an emergency consolidation of this Cork pavilion in Madrid. And we didn't have the means. This was a very small project. It had to be done very fast. So we tried to do like an in-house study of these very small structures to determine which would be the least invasive intervention. So we did this on our own, and this might not be the most thorough like analysis of heritage values, but it really helped us determine like what would be our conservation strategy. So when we understood by means of archival research, studying how this Cork pavilion was fabricated, and studying the typology of this type of constructions in gardens across Europe, like we determined like which values were more important in the building, and we wanted to try to our intervention to respect those values. So what we did is that we analyzed different structural interventions, which are like in the horizontal rows, and we tried to study like the influence of these interventions on the significance, on the heritage values of this building, the potential risk to the object, the impact of the interventions on the reversibility, impact on the durability of the building, how difficult they were to implement, and the cost of the intervention, which is always very important. So by doing this analysis and taking into consideration several interventions, like how will they be affecting the structure, this helped us choose what we consider was the least invasive one, or the optimal intervention. Our responsibilities as cultural heritage stakeholders are like both being sensitive to cultural heritage values, know that they exist, identify them, and if we need someone, like ask for help if possible. and take them into consideration when we are designing of heritage interventions. But we also need to recognize the intangible heritage that we've discussed and the impact that our decisions have on it. And this is something what goes most often overlooked. So how do we identify these values? How we did this little table, no? How these values manifest in wooden heritage, or can we identify intangible heritage in a physical building or object? What characteristics of buildings, wooden buildings, need to be protected? So in order to do this, when we approach a timber structure, we identify the characteristic features of the wooden architectural heritage that are characteristics of wooden architectural heritage. So we both have tangible features, the same as we have like tangible heritage and intangible heritage. We have tangible features and intangible features. So tangible features are like very easy to locate. These are like material characteristics, the species of the wood that we are working with, the textures, how the timber was processed, how the carpenters worked it. No, that usually leaves some marks on the surface. Decorative finishes, surface treatments, and even the presence of hardware like iron or steel hardware as part of the timber structure. And we also have many intangible features. This could be the traditional constructive knowledge and skills, silviculture, or the knowledge of like growing trees, so they are better suited for their structural functions, and also knowing to choose the trees to fell them and turn them into like structural elements. The provenance of wood, when we study like wooden species and we locate wooden species in a building that is not a local species but has been brought from afar, that usually talks to us about like commercial relationships or like other things that might have been happening between our place of construction and the place of provenance of the timber. We also have hidden marks, and that's in the middle at the left. In many places, carpenters would mark on the timber elements notes and symbols to assist in construction and assembling the wooden structure, and that tells us a bit how the construction process was made. So when we see this, we usually try to mark them. Also, the structural resisting function of wood is very important, because very often engineers would neglect, because of lack of understanding or lack of trust, the structural resistant function of wood, and they would just build a new steel structure within the timber building, ignoring the timber structure in itself. And like the fact that our structure can be a functional structure is also like a heritage value. The use that these buildings have, also the scientific knowledge that is needed in order to have designed these structures, because many of our current wooden heritage was already like designed, no? It was engineered, the timber structures. And what I like a lot is the picture to the right, in which I have highlighted in red part of a text and in blue another part of the text. So this is about our technical language. In red, we have the description that a carpenter makes about a timber roof in Spain. And the blue area, it's encircling like the footnotes of all the different terms, explaining all the different terms that he is using, because our technical language is part of our heritage, and it's very important for us as professionals to incorporate the traditional terms into our projects, because we need to promote the use of this language, not only because it's accurate and it's very precise and it's the correct way to refer to things, the one that would lead to less misunderstandings on site, but also because it's also part of our heritage, and we want to keep that heritage alive, because it's very particular to our architecture and to our society. So how, once we have gathered all this information, how can we draft an intervention methodology? So usually, like, methodology should be tailor-fitted to its case study. We cannot have just one single methodology that would be valid to all types of wooden heritage, because the wooden heritage might change a lot in different cases. We need to adapt it to the heritage values and the features of the structure. But once we studied, we should just prepare like a list of things that we need to understand of the structure, a series of objectives, and with that plan an integrated approach. I'm just showing here like several different tasks that were used to understand a historic church north from Madrid in Spain. And these different tasks might vary a lot from one building to the other. However, there are guidelines, and there are actually very nice guidelines that are common to like all types of wooden built heritage. And I think this is a very useful document. This was prepared by ICOMOS International Wood Committee. For those of you that don't know this, like ICOMOS is like a consulting association to UNESCO in matters of heritage. And they have a special like committee regarding wood heritage. And like in 2017 in Delhi, actually, like these principles for the conservation of wooden built heritage were adopted and approved. And it's a very nice guideline that if you are ever working on a historic timber structure, this is very nice to follow if you are having doubts on which approach to decide, or like if you need to double check if there was anything else that you could do to better understand your structure. I recommend this. Is a very nice read, and it's also like available like in their website to download in different languages. An important concept when we work in heritage structures and also like in wooden heritage is the concept of minimal intervention. No, I think Javier already discussed about this. No, like we want our intervention to be safe and not too invasive. No, so that's basically what minimal intervention is. No, it's the minimum intervention that meets the structural requirements in order to ensure the least harm to the heritage values that we have already discussed about. But how do we determine which intervention is the minimal? This is not an easy task. This is very challenging. So we can only discuss about general recommendations to implement in order to try to find what the minimal interventions would be. We firstly need an integrated plan, that we need to try to aim to meet architectural, structural, and functional requirements, because the three of them are very important. And in order to do this, we might need a multidisciplinary approach, and we need to engage as many specialized professionals as required. Each building also is unique, and sometimes what has worked in the past for a building might not work for another one. So bringing in specialists is the best way to ensure that mistakes don't happen. Also, we need exhaustive data gathering. As much information as we have about the building, as Javier was mentioning, the most accurate our assumptions or interventions will be. Also, the precise analysis of structures, evaluate many different case scenarios, different interventions, not just one underperformance, but sometimes we might need to do analysis for different types of interventions in order to determine which one of them is the least invasive. And as Javier already mentioned as well, the use of calibrated models in case of analysis, because we want our analysis to be representative of the reality. If we do a lot of numerical calculations that are not representative of the reality, they are not that useful. Also, we need to use compatible materials that will not harm the existing materials of the building. I just bring a very simple visual example. To the left, I have made a little square with the size equivalent to what's the modulus of elasticity, which is an important mechanical property of timber. This is an average timber. And to the right, I have painted the modulus of elasticity of steel, because very often timber structures are reinforced with steel. But as we can see, steel is 20 times higher, the modulus of elasticity is 20 times higher, and mechanical properties are not the same. And also, when it comes to behavior due to temperature or under humidity, these both materials do not behave in the same way. So when we work with historic timber structures, the most compatible material is wood. And this, believe me, is not that often done. No? Like many times, engineers resort to to steel or like concrete in order to reinforce the historic timber structures. Not only is good for compatibility to use wood, but we also need to use wood in the proper direction, because as Paul mentioned, materials like timber do not have the same properties in all the directions. So we also want to make sure that when we use timber, like we use it in the correct way. So I'm just showing this as an example of how careful we might need to be when detailing the repairs, because we can replace a missing part with a piece of timber, but if we put it with the grain of the wood in the wrong direction, this intervention might not be durable, and we might need to repeat it again in 2 or 3 years. So that's just what I wanted to talk about historic values, and now I will go very quickly through different testing methods that we have in order to increase and improve our knowledge of historic wooden structures. When it comes to testing structures, we have different methods according to the level of intrusiveness in the structure. We can take a piece of the building, bring it to the lab, and break it to see how much it resists. That's destructive testing. I will not be covering this because this is a task that you can ask local laboratories. And an important thing about this is that once you take a piece of element of the structure and you take it to the lab, you no longer have that piece of structure. So we cannot always do this. This is going to give us information that is reliable for the piece of structure that we destroyed. But in heritage buildings, very often we cannot just take a lot of pieces and take them to the laboratory. So that's why minor destructive testing and non-destructive testing are very useful. Minor destructive testing usually they do holes or very minor damage that sometimes it cannot be appreciated at first sight. So it's also useful and very much appropriate for heritage building as well. So the first two techniques that I want to show, that this is very obvious, but this geometrical documentation techniques, because sometimes by doing a very thorough geometrical survey, we can study aspects of structures that might go unnoticed if we do a simple inspection, just a visual inspection. If we obtain an accurate geometry, we might be able to study deformations in a building and study if we have an edge of a building that is tilting and how much. If we quantify deformation, it's also very useful for us in order to perform calculations afterwards. In order to capture and collect information about the geometry of the structure, we can for example, do photogrammetry, which is a low-cost technique with just photographies. We can create a model, a 3D model of an object or a building, on which we can later measure and consult details and other information. If we need a more accurate and high detail documentation of the geometry, we can also do laser scanning for more complex structures. This is the same structure as before, we using the same methodology. And we can also do wooden species identification. This is done in order to understand what's the wood species with which our building was built. With a very small piece of timber, we can take it to the lab, we slice it, we taint it, and we look at it through the microscope. And by comparing this at microscopic level, how this timber looks like, we can understand what is the species. And this is important for several reasons, not only because it gives us knowledge about whether if the species is local or not, and what is the typical resistance of this specific wood, because sometimes this is already studied and there are already published values for different species, but also this is very important information that can be used for different other testing techniques, because a wooden species is very important and it has a lot of influence on other material parameters. We can also do radiocarbon dating, and I think Ingun showed this image already in her presentation. But for those of you that maybe were not here, some samples were taken from the Sanskar temples and from timber elements, and with radiocarbon dating, they can give you an estimation of when the timber element was cut, the tree was felled in order to transform it into a structural element. Thank you. We can also do dendrochronology. Dendrochronology is based on tree ring dating. So like each year, a tree grows a new ring. So with this, we can study the ages of trees, and not only by counting the rings that they have, but also because each year might have been different in a region, or like you might have more rain, or there was a drought. So dendrochronology is the science that uses the tree rings in order to establish a chronology in a region. So later, when you extract a very small core of a wooden structure and you compare it to an already established chronology, you might be able to very accurately know when the tree was felled. We can also do moisture content measuring, and this is really important because moisture content measuring, which is like the amount of moisture that we have inside of a timber element, is telling us if this timber element might have been exposed to excessive moisture, or if it's prone to have, or if it has excessive moisture and it's prone to have like material deterioration in the future. But it also it's also important because moisture content affects the resistance of a structure, and all the parameters that we might measure when we study timber structure are very much related to the moisture content. So measuring this will allow us later to calibrate our assumptions and determine what's the real capacity of that structure. We also have piloting, that this is like it's a device that this is a needle that it's spring loaded, and we can hit with this the same force on a timber structure, and then we measure how much the pin goes into the depth of the wood. And this can tell us a lot about the condition of the timber element and also about the density of this existing timber element, because we can measure how much the element is opposing to this needle penetrating its surface. We also have a more technical version, that is the resistograph, and it's a very long needle, and this was first used for investigating trees before felling them, but we can also use this for structures. And we can measure with the resistograph the resistance that it's encountering the timber while we penetrate. So we can study different depths of the timber element and know if we have hidden decay inside the timber element that we cannot see from outside. We can also do dynamic testing, which is like placing some sensors on the surface of either like timber elements or the totality of a structure of a building, and measure how the structure naturally vibrates. And this can help us calibrate our structural models, or also tell us other information, such as how is the connection of a timber beam at the ends on the masonry walls, whether like it's acting as simply supported, or if it has some sort of if it's fixed in the ends. That can help us inform the rest of our structural analysis. We also have acoustic wave propagation. Javier has already talked about this, so I will not go through it again. And that's all for techniques for timber testing. I only just want to finish the presentation mentioning that, as Javier said already, that gathering data is very, very, very much important when working on existing structures. Because if we compare like the degree of the knowledge that we have of a structure with and without data gathering. Here you can see testing, but I'm talking about everything, just archival research or geometry documentation. We can fight the uncertainty that it's intrinsically linked to historic structures, because we don't know how they were built, the material properties of the buildings. The less research that we do, the more uncertainty we have. And the more data that we gather, it will help us have less uncertainty. So more uncertainty leads to more conservative assumptions and a more invasive intervention, while having less uncertainty will lead to more accurate assumptions and minimal intervention. And this is optimal for heritage conservation, but also for projects that have a limited budget. And this is something that it's really not fully understood because the more you invest with resources in the early stages of a project, and the better you know your historic structure, it's more likely that you will be spending less money in its repair, because you can do the minimal intervention and spend less money also on construction. So sometimes, like, advancing part of a data investment at early stages will not only can be a positive can be positive on the budget of the project, but will also help us protect of heritage structure. So this is all. Thank you very much.
We have some time for questions now, if anyone has any questions.
I was interested in those surveys of all the buildings in a town, and I was wondering, like with the Yushu earthquake in 2010 in Tibet, and there's so many recent earthquakes in Iran and Turkey, is there any study that took that survey of the probability, these are the high-risk buildings, these are the low-risk, and then get the high-resolution satellite imagery of a day after the earthquake, or maybe 1 week after the earthquake, and then actually compares which ones failed and which ones didn't?
Well, I think that's very interesting. But I don't know if they have done it with satellite imagery. The way it's commonly done is with field surveys. Every time recently, maybe before you didn't use to do that so much, but now every time there is an earthquake, there is post-earthquake reconnaissance missions. And there they try to get data of all the buildings in a detailed way. They individualize all the buildings that suffer damage, what were the characteristics. But I am not aware of that, but I think might be interesting even in compare if it's possible to also gather all this data with satellite. Maybe there should be some people working. There's so many research now with satellite imagery and all the things that you can get with that. But definitely it's very interesting. I don't know of it, but I hope somebody's working on that because I think it has a lot of potential.
Hi, I'm Prabhu, and thanks for the great presentations. So just a earthquake preventive culture, I think Mr. Ortega. So what do you think of Japan as a culture, as wooden structures to prevent earthquakes? Do you have any ideas on that?
I don't feel very comfortable talking about Japan because I don't know it. I mean, I know the myth that, and I guess it's true that it's a very well-developed country in this context. They have developed a very high and earthquake-resistant system, and I think they are very good on that. But I don't know. I don't know if you know more about the wood conservation. I don't know about that, so I'm afraid I won't be able to give you an answer. But I'm sure. I mean, this is a country that is fully exposed to earthquakes during the whole history. So I'm sure they have developed very good traditional earthquake resisting systems, the same way that now they are developing very high-end modern earthquake resistant system. So I don't know, but I'm sure they have. I don't know if you know maybe.
Yes, I don't know much, but I can say that they do have, as Javier like showed in his presentation, like local seismic culture, no? And at least in timber structures, historic timber structures, some of their joinery has proved to be like very effective in case of earthquake and in order to dissipate energy. So there are like actually very interesting YouTube videos in which you see these joineries and these structures being subjected to earthquake loads, and some of them at least seem to work very well.
Thank you, Marietta and Javier. And thank you to all our speakers over the past 2 days, and everyone for attending in person and online. I think Geshe Doctor will now say a few closing words for the weekend.
Thank you.
I must say that we had two extremely fruitful afternoons. And hence I would like to express my deepest appreciation to Nyandak and team and learned, experienced scholars who came all the way to share your knowledge. It was amazingly enriching. As a senior person, let me try to summarize a little bit. The way you organized everything was perfect because the first day was on architecture, second day was on earthquake, which are very closely related, because if you don't have the proper architecture style, earthquake will kill you. So that's probably what you were trying to deliver. In the Buddhist Tibetan tradition, when we talk about architecture or especially construction, we talk about physical construction, verbal construction, mental construction. And you touched about the tangible, intangible. So that is actually related to the fact that the whole world is interaction between the physical and the mental, which is basically the tangible and the intangible. So that's a great summary that you are making. And then while we are talking on this point, we talk about the changes that needs to be made of the traditional versus the modernity. So there, the Buddhist teaching that everything is in a flux, and the only thing that is constant is change itself. So the change is not necessarily negative, but can be positive if you know how to flow with the current, as we say. So you're basically talking about how to flow with the current, take the best out of the traditional knowledge and also use the best out of the modern knowledge. So that's basically what we are trying to talk about. So change is extremely important. And when you talk about change, that reminded me also the Buddha's teaching that in fact, all of our suffering comes from ignorance. Ignorance of interdependent origination, ignorance of change, ignorance of architecture, thereby. So we unnecessarily suffer because of lack of knowledge. So that brings to the point that removing ignorance, here in this case, the destructiveness of earthquake. You should know about it, remove this ignorance, and you will be safer. And of course, when we talk about the change, we also touch on the, as you use the word, minimal intervention. What is to be preserved, what is to be protected, what is to be improved, things like that. Then we touch on the topic, what is sacred, how can you maintain this sacred identity and things like that. That reminded me one teaching by His Holiness where he repeatedly said that the images, holy, so-called holy images in the temple, not become holy by itself. They are made holy by the people who are practicing. So the so-called sacred heritages are sacred because somebody lived there, a great teacher or good people who lived there, practiced, they put their positive energy there. That is called sacred. And similarly, you have also many places which is really like, I don't know which English word you have, profanity or something like that, something that is not sacred, you know. Because when I visited once place in Moscow, His Holiness said, today my meditation was not at all clear. It seems a lot of bloodshed has taken place here. A similar Lama, Khamtu Rinpoche, also had the same experience there. So the place can have positive energy, negative energy, depending upon how people, you know, use their way of life there. So therefore, there are things that we must maintain. There are things we need to change. Don't just cling on to something that saying that this is sacred tradition. It may be just a cultural clipping of no use, you see, maybe redundant. So we need to get rid of those things and then get the best out of both the traditional and modernity. And in fact, many people have a lot of misconception about modernity. Modernity is not just big buildings and shiny roads, you know. Properly understood, modernity means equality, interdependence. All those great concepts are there. But today people think modernity means big buildings and shiny gadgets, you know, and that is not modernity. So there is actually no contradiction between the traditional and modernity. At the end, without taking much long time, because we have been sitting here for so long, as I said, all problems come out of ignorance. Ignorance of all kinds, ignorance of the risk of earthquake, whatever, all kind of ignorance. So we need to, the more we remove those ignorance, the more there is likelihood of remaining safe and happy and healthy. Of course, at the end of the day, we all have to die, you know. Kandunneja chive mezupe sajo dine yoba mainde panang name jasu nam name ruva nam yisib the shungname. It's a teaching by Buddha where it says at the end of the day we all have to die. Wherever you live, there's no place where you will not be touched by the death. It's not on the earth, it's not amidst the sea, it's not amidst the mountains. Somehow you have to die. But that doesn't mean you die. You should die before before the time comes. So in Buddhist teaching, we talk about three kinds of death. Sonam seni Shiva, the death because of lack of merit. Se seni Shiva, the death because your lifespan has ebbed out. Then third, Yangamavame Shiva, that means death because you have not removed those accidents and other obstructions which you could remove, but you did not remove. So protection from earthquake will prolong your life if you are aware of that. So therefore, I must conclude by saying ignorance is the root cause of all problem. That is true, but it is not just ignorance, but inaction. So we need to now come out and do something, whatever is possible, which you are all doing. So thank you very much for that. Thank you. And thank you for everybody who has paid so much good attention and participated. Thank you, everybody. Thank you, everybody. I would like to present Khadag and some books to all the presenters and all the teams from Nyandak family. Okay, I would like to Khadag, the presenter, someone.
Dr. John Harrison and Dr. Amundsen.
And I thought about what books I should give, and all of you seem to be very focused on the Kuge area. So I'm presenting these two books, The Ancient Tibetan Civilization and The Brief History of the Kingdom Kuge. Then, of course, library.
And Tenzin Yindakla. Oh, John Harrison.
Yeah, go home.
Dr. John. Paul LaRoque. Professor Carl Raeva.
Oh, Dr. Cole, the team from Sarah who are doing this map on Tibet, they will get you. Because you have so much expertise, and I really highly recommend it that they seek your guidance. Thank you so much.
Marietta Garcia. Javier Jerez. Tenzin Nyandakwa.
Which is also. For the Tibetans, I have Tibetan books. And also related to you, survey of Spiti area.
Chuyang Ma.
Sangma. Spiti Nyandak is Sangma Pecho Foundation. Such a wonderful team.
Ditchin Sogela.
Oh.
Gangchen Doma. Pasang Tashila. Terry Yang Chinla. Lakba Doma. Ngawang Yeshu. And Wangila.
Come on. Thank you. Thank you.